hope I scheduled the event right. Hey, what's up, Johnny? That was a quick snipe. Analysis work. What's up, egg enthusiast? Glad to have some Europeans here. It's classy. Your eyes do not deceive you. We're looking at the definition of a pointwise limit, which seems straightforward enough from the example they provide here. So this is kind of interesting. I'm not really sure, I guess, what they're going for, like, with pointwise. For each n and n, let fn be a function defined on a set A to R. The sequence fn of functions converges pointwise on A to a function f if for all x in A, the sequence of real numbers fn converges to yeah, it's interesting because it's like a multi-variable function in a way, kind of like f. It's got x and n as parameters. Fn. Let me make sure I have this. Converges pointwise on A, so it converges on a set to a function if for all x the sequence of real numbers f of n f sub n x converges to f of x. Okay, that's kind of weird. You gotta Anki card that, not gonna lie. Yeah, you're probably right about that one. Let me do that real quick. Pointwise convergence. We write fn to f. So this expression is helpful if there are any confusion on whether x or n is the limiting variable. Last expression. I would oncify that, but I think I don't know. I'm kind of rehauling that whole, or overhauling that whole, the whole Anki workflow. Like there's an open source version of it called Hashcards, which uses plain text that I want to support types first. It's a whole thing, and like, yeah, the problem with oncifying like big math definitions is it's not very fun. I think the way you have to do it is break it down into little pieces, and I'd rather just churn through the math. It's just the obvious notion of convergence, i.e. the limit of the function at a point is just the limit of the functions on that point. Yeah. Okay, so the example they give is n plus cosine nx over 2n plus 1. Quitting Discord. N plus cosine nx plus or over, what was it, 2n plus 1. So if n is going to infinity, I guess we can split these two. Should probably have a slightly different setup when doing this. Let me see if I can, just so I can get visuals on this better. It is called hash cards. It's quite cool actually. Basically, I was just like starting to set it up. It's like the problem with someone put me onto this. The problem with it, or the problem with Anki, I guess, is there's a real art to doing it in a way that you don't like crash out and fucking fail at it, which is very easy to do. You have to make it very fun. You have to actually make it very effective. So very atomic little cards, and there's like, I just haven't put the work in yet. So I think it'll like slow me down momentarily more than it'll help me, but over the long run, like exponentially, I think it would be a lot better. And how do I learn English fast and effective? Anki, honestly. I was about to mention hash cards. I sent an email to you a couple days ago. That was you. Thanks for the recommendation. Yeah, I did get that off of your. And also for anyone asking about the Discord link or whatever, that will be dealt with momentarily. Like the way we're gonna handle that, especially for people that write emails, is I just need to get like email access to people on the hiring team. Okay. So we could break this up, definitely. Into n over n over 2n plus 1 plus cosine nx over 2n plus 1. And we're obviously, each of these we're taking the limit as, because they want us to find the pointwise limit, and goes to infinity. And I guess let's just put like square brackets around this whole thing. That's really probably a very janky way to do that, but and then that'll just be like what, 1/2 plus probably 0. So just 1/2. Wow, the chat's getting active already. I'm one of your classmates. Thanks for the homework answers. No way. Which one of my classmates? That's wild to think about. There are like, I don't know, I've ran into 3 or 4 people that know who I am. Oh, I'm looking like yeah, that was damn. Do you have a new keyboard? It's very prominent. No, I don't. Sorry if my keyboard is very prominent. What a troll that was. Okay, maybe I'm not the most BS averse. Hold on, wait. This is not the correct answer. Man, why is everyone's hardcore messing with me? I forgot how hard it is to get work done with. Okay, so find the pointwise limit of x. For given epsilon, construct a uniform epsilon ball such that the nth term. What is this notation? It looks very familiar to the definition of just convergence, but or the definition of a limit, but sequential limit. The distance sub infinity. For a given epsilon, construct a uniform such that f of n minus f is less than epsilon. You can use an arrow limit instead of this weird limit brackets. What do you mean? I like this though. Subsolar. Okay, so we're converging to the constant function, like this weird infinite distance double bar thing. We're gonna get like whatever this is, let's copy to the equal sign minus, right, because it's f of n minus f less than for any n greater than sound is pretty quiet. Why forward my name a crayon? Is my like properties? Oh, I'm using my Max microphone instead of my dedicated one. All right, I should sound quite a bit better now, and the keyboard should be slightly less loud. Oh, it's no. Math streams are back, yeah. Unfortunately, like, as fun as it is to just do 500 different things, like, every once in a while, you just gotta actually do some work. For given epsilon, construct a uniform n. What do they mean by construct a uniform n? Construct a uniform n of epsilon? Do they want, like, do they want a function in terms of epsilon? My real analysis is getting rusty. Like, infinity norm definition. Hey, what's up, Reams? Norm, non-negative real numbers that behaves a certain distance from the origin. But what's the infinite norm? Infinity norm. Maximum norm, infinity norm, or supremum norm? That's only for the finite case. How can you have a finite case of the infinity norm, bro? What even is math? L infinity norm? Oh, here we go. Definition of the infinity norm. Finally. So it's the max. It's the max of a bunch of, what is the x1 through xk? Of the L infinity norm. Why is it L too? For a function, it should be the supremum x and r f of x. Okay. It's only for the finite. All right, cool. Yeah, I'm not gonna lie. This might be a rough homework to finish because I've been like struggling to pay attention to class. So in your case, f of n minus f is equal to the supremum x in R the supremum of f of n minus f of x of n oh, the supremum sub x in R of, okay, cool. So constructing uniform n of epsilon. This notation is also a little new to me, but did they just mean like a function of n in terms of epsilon? And that's an interesting notation for that, but yeah, just n in terms of epsilon. Cool. Okay, so we basically, how are we gonna get that? Yeah, Johnny is carrying. um, yeah. When will you see me taking RL? I mean, Troy's already kind of doing RL lectures in the server, and there is a project I really want to do RL on, but what's the deal with this symbol that people keep sending? Like, oh, it's just this weird emoji encoding. I see. Um, okay, cool. Yeah, yeah, yeah. Um, so I'm not sure I understand this infinite distance concept or this supremum distance. Like, how can you have the supremum x and r of like this isn't a set though. Um, it's like a discrete point, isn't it? Um, let's see. So we're looking for an n to which an n greater than that n will imply. So yeah, the big N needs to be in terms of epsilon for sure. Big N in terms of epsilon. Such that that inequality will be true. Man, yeah, my real analysis skills are a little rusty. This will be good to get back into the flow of streaming this every day. Construct a uniform. Such that if you let x vary, then the set of all absolute function values, you get the set of all absolute function values, and you take the supremum of that. If you let x vary, you get the set of all absolute function values. Oh, I should have maybe wrote down the supremum more carefully. Yeah, what the heck, Johnny? Um, uh, supremum g of x, x and r. Oh, okay. Yeah. Um, okay, so it is just an epsilon delta proof, but that's interesting. So as you let x vary, you get the set of all absolute values. As you're letting x vary. let G so the supremum as X varies of this set. But how much does this distance function actually like how much does it actually affect the algebra you need to do? Because if it respects the triangle inequality, I guess let me think like okay, let n, we're gonna need n equal to something. My brain is rusty AF. It's gonna be equal to something in terms of epsilon. Now, like, how do we combine these two fractions or make this easier to work with? Like, how will this pare down? How will this be simplified into something usable? I'm a little fuzzy on those implementation details right now. Let's see. Pointwise limit. Oh, that's a nasty one. Like, this isn't super just, oh, the triangle inequality. Assume sequence of continuous function. Okay. Wait. What is this? Continuity of the limit function. No, that's not really what I'm looking for. This is like honestly quite a basic epsilon delta or just epsilon proof, but I'm kind of stuck on what to do for the algebra. Be arbitrary, let any Yo everyone, there's a lot more chatters than I expected actually, which is awesome. Okay. What's the general approach though? Let me answer that on coming up with these coming up with a value of n. It's like seeing how simple of a representation of epsilon I can get until I get something like, I mean, so add a half to both sides. Shouldn't n go to infinity? yeah, don't let n equal epsilon. Yes, n does go to infinity. I just like put that in there as a stopgap. But n is gonna be, yeah, man, I am. Yeah, I'd hop in a VC because I'm rusty on analysis. You can rewrite your left-hand side as one function. Rewrite your left-hand side as one function. What do you mean by like multiplying? We would get like 4n plus 2 on the bottom. Fraction. Common denominator. Yeah. One sec, Johnny. I do want to try to figure this out a tad bit more. Yeah, that's, I guess, a pretty reasonable approach. Oops. So, like, yeah, that could be, this 2n plus 1 could multiply by 1/2, so 4n plus 2. And then on the, oops, why did I like make all that effort and then change the wrong thing? 4n plus 2. And then on the top, we would have 2n plus 1 additional, but we'd be subtracting it. So minus 2n minus 1, so we get minus n minus 1. And oops, that. Does that help a ton though? Confused with this trig function, I've never seen this. Let me call up my math expert. Where are my headphones? Okay. Hey Johnny, how's it going?
Hey, what's up?
Not much. I'm just man, I like was slacking on doing math homework for a while, and now I'm like cooked.
Yeah, it's you have to get back into it, but it's good. Are you feeling better already? You said you had a fever, right?
Yeah, I am. I just chugged a ton of
Yeah, that's
tea.
good. Okay. Um, Let me just quickly find my glasses. Otherwise, it's not gonna end well.
Cool.
Um,
Sup,
did your
LMAO?
did your teacher like in class even introduce this infinity norm?
No. I yeah. Um she didn't, but also like I did miss a couple of classes recently.
Fair enough.
Yeah. So it's totally
Fair.
possible.
Yeah. Um. Okay. So so how are you feeling on the definition of all of these things?
Um well, I don't like definitionally, I just read through like pointwise limit. It makes sense to me.
Hmm.
Um I guess I'm just confused about it. It's been like so long since I've tried to do an epsilon proof.
Yeah,
Like
I mean, yeah. This first thing that you did, that's indeed about this pointwise convergence. So showing that this sequence of functions converges pointwise to the constant function 1/2, right? That's good. And now, I mean, they worded it like a bit weird, to be honest. Like it's a bit weird, but basically, what we're going to show now is that not only does it converge pointwise, but even uniformly, which is like stronger.
yeah, okay. Yeah. Which means there's like
And how
a single upper bound epsilon, I guess.
yeah, we can find this. I mean, that's what's going on. The thing is, we're going to show that we can find this capital N uniformly, so without reference to x. Like for given epsilon, we're going to find one n which works for all the x,
I see. I see. Gotcha. Okay.
right? Because if you just show pointwise convergence, then capital N would be allowed to also depend on x.
Um, is that always possible, or is that just because our x here is contained inside like a bounded function?
Well, actually, it's special in this case, and actually, it's very special because x is not like on a bounded interval, right? X can be any real number. So this kind of says like that this convergence of this sequence of functions is in some sense, I don't know, like strong or fast or however you want to describe it, like because this x can be over like this whole infinite interval, but still this function converges uniformly.
Yeah, I see. I see. Okay.
So yeah, this is not something automatic. It's quite special, and it's basically so if we think about like we have this function f of n minus f, right? We want to show that this infinity norm uh, it gets really small if n gets big. That's the point, right? So um, what is this infinity norm of this difference function? It's as you let x vary, you consider all these function values that you get in absolute values. So it's like because we're considering this difference, right? F of n and f, we're considering like in absolute values. If we let x value vary over the whole real line, how big can this difference of our limiting function f and one of those functions fn ever be? Like what's in some sense the maximum? Because we don't know a
Yeah.
priori if this maximum exists, so we call it a supremum.
Yeah. Okay. Okay. Yeah. It's
So, and in some sense, yeah, saying that this goes to epsilon means that you can find like an n big enough, this capital N, such that this supremum norm gets very small. It just means that wherever you are on the real line, the difference of this function is everywhere like very small.
I see. Yeah. But I guess what I was asking is like the x here, it's like inside of a cosine function, so it'll be
Mhm.
between like -1
Exactly.
and 1.
Yeah. Oh, yeah. Sorry. Yeah, I missed that. Yeah. No, exactly. That's more or less, yeah, how we're gonna do it. Like, because this x is in a cosine, it's, yeah, that term that depends on x is gonna be not so big, and we're gonna divide out by like this 2n plus 1, which does get very big as n gets big. So exactly, that thing is gonna go to 0 very fast.
Yeah.
Yeah, and that's basically all. So
There is a typo.
okay, now that we have like I think like a nice understanding of what's going on, I feel like we can just start using the definitions. I mean, to be honest, it has been a long time for me, but I think that this infinity norm is like an actual norm. So I think the triangle inequality should hold.
Yeah, on that Wikipedia page it is.
Yeah. So, because how, like, I mean, you can put it all into one fraction. I think that's probably fine, but like,
Yeah. Hello.
yes, hello.
Sorry, I think the for some reason my Discord client corrupts audio after 30 seconds.
Oh. Yeah, so yeah, what I was saying, this n over 2n plus 1
Mhm.
goes to a half, and this cosine nx 2n plus 1 goes to 0 quite easily, hopefully both.
Yeah.
So I think that's a nice way to split it. Like, we consider this n over 2n plus 1 minus a half, and then we also have the cosine nx over 2n plus 1. And we know that those two things both go to 0. So I would use the triangle inequality to split those up, and then show separately that we can bound them by, let's say, epsilon over a half, right?
Yeah, okay.
And then the sum is bounded by epsilon. That seems like to me like a good divide and conquer type strategy. Like, so we don't have to worry about too much thinking.
Yeah.
Mm,
Which is the worst.
exactly. That's what we desperately try to avoid.
So splitting it into n over 2n plus 1 and cosine nx.
Yeah, so, but we still have to worry out the minus a half. So I would term the group, the minus a half together with the n over 2n plus 1, because n over 2n plus 1 minus a half, whole thing in absolute values, that goes to 0. We know that, or we can show that quite easily. So I want to show that that goes to 0, and then just the cosine nx over 2n plus 1 in absolute value, show that that goes to 0. Or I guess in the infinity norm, I should say.
Yeah. So we could do a bit of a split here.
Yeah, I think by the triangle inequality, because I'm pretty sure this thing is a norm. I don't think about these things very often, but yeah, it should be. And also, yeah, one nice thing is like the left one that we have, this n over 2n plus 1 minus a half, it's completely independent of x.
Yeah.
So this infinity norm is really, really harmless, right? Because it's like a supremum over all x, but our thing is independent of x. So that's also really nice.
Yes.
Um,
We would have this is less than
exactly. So if we can now basically, right, we need to find some capital N such that this final inequality holds with this epsilon. So if we find some capital N where each of those terms in the sum is smaller than epsilon over 2, then we can just take the maximum of those two capital N's and choose that, and then we're guaranteed that the sum is less than epsilon.
Okay, so that's interesting, using like the max to have two different.
Yeah, it's kind of this like encoding, like, because if we have, let's say we have an n1 which works for the first one, what is this saying? It's like for every small n bigger than n1, it's gonna work. And if we have an n2 for the other one, it's like for every small n bigger than n2, it's gonna work. So we need to come up with some new, let's say n3,
Yeah.
where everything bigger is gonna work. So yeah, just to ensure that both inequalities hold, we just take the maximum of the two, or you can take the maximum plus 100. It's all, yeah. It's not really,
I
it
see.
doesn't really matter what.
Okay, so one of those terms will just um, go to 0, and the other one, like, what would you bound it by? Epsilon over 2?
I mean, we will both bound both of them by epsilon over 2, I think. Because right, so like if we have both of them bounded by epsilon over 2, we're happy by this maximum argument. But so we can kind of think of like we're really taking the limit now as n goes to infinity in some sense,
Yeah.
because this infinity norm thing just kind of gets rid of the x dependency. So what we're left with after taking this infinity norm will be something only dependent on n. And we want to show as n gets big that this thing gets epsilon over 2 small.
Yeah. Yeah, okay. This is kind of weird with the two variables, but I see.
Exactly. Yeah.
Yeah.
Kind of you have to carefully think about it.
Yeah.
Um, so we can like, but the nice thing is like we can treat them now more or less separately, right? For example, we can just first treat the first one, this n over 2n plus 1 minus a half,
Yeah.
and there we had this nice, we already mentioned, right? This whole thing is completely independent of x. So taking the so taking the infinity norm of this thing, it's like a constant function, and we take the supremum over all the values of a constant function.
Hmm.
Well, that's just the value of that function.
Right. I
Of
see.
course,
I
we say
see.
so. Yeah, so this first one is like really nice and easy. So the infinity norm of this first term is just the absolute value of n over 2n plus 1 minus a half, right? So we want to choose our capital N such that this gets less than epsilon over a half. And right, and at this point, it's exactly the same as doing an epsilon n proof, right? Showing that this sequence n over 2n plus 1 converges to a half as n goes to infinity.
Yes. Yeah.
I think at this point, yeah, it's literally the same. So you could even say like, yeah, I mean, at this point, maybe in the real analysis course, you can say just like proving this is equivalent to proving that this thing goes to infinity, or you just write out the explicit thing. I think that's also fine.
Yeah. I didn't think about doing that, but yeah. Um, and what value of big N are we going to be?
So for this first one, I mean, yeah, this is going to be it's going to be something dependent on epsilon, right? So at this point, we can do it like a usual epsilon n proof. Like we're going to simplify this left hand side, this absolute value, I would say a bit. Yeah.
Combine
So
numerator and denominator?
simplify.
And is it fine to have to n on both sides? I mean,
What do you mean with n on both sides?
um, like to if we're simplifying. Oh, actually, I guess are we going to at some point we know this is like converging to 0. But are we ever gonna like make the actual substitution?
We're not gonna substitute for 0. We're gonna do this like purely formally in epsilon language, if that's what you mean.
Yeah.
Like we are gonna just use this. We're gonna do this small argument that this gets that we can find in n1 where it's less than a half. Less than epsilon over 2. And we're gonna do a similar argument for this cosine term, and then we just get that their sum by this maximum argument that their sum is less than epsilon. So we're never literally gonna put in 0 if that's what you mean.
Right. Yeah.
We're really all doing it in epsilon land.
Yeah.
Um,
Gotcha.
hmm. um, but okay, yeah. I mean, yeah. At this point, it's just find an appropriate n such that this n over 2n plus 1 minus a half in absolute values gets pretty small.
Yeah. Yeah. Which yeah.
Yeah, for this we just have to yeah, the usual business. Try to simplify the fraction a bit. Because you wanna express this and then like kind of work backwards. Like we want this absolute value to be less than epsilon. So suppose we have that and try to work backwards.
Yeah.
And see what condition we get on n in terms of epsilon.
Right. So combining this, I mean, we can multiply by the reciprocals and get, I mean, I guess just I'll do that out
Wait, sorry, what?
like to combine these two into a single fraction.
Yeah, I mean, what you did probably would like to make it, yeah, 4n plus 2 sounds reasonable. Just make the denominators equal. I think probably a smarter way to do this.
Yeah, I'm also like after we achieve that, I'm a little confused on where to go next.
Achieve which part exactly? Until
After we combine those two, um,
I mean, in the end, yeah. I'm also because I've also not thought about these kind of problems now for a bit. But I mean, what's the easiest way to show that this? Because what will we get once we've combined them? We'll get like 2n plus 1. You'll get like, yeah, probably that won't even be that helpful. But can you at this point use like limit rules and stuff?
yeah, I would imagine so. I mean,
Because I feel like we can do some trickery to avoid coming up with the explicit n and just saying that it exists with the limit rules.
yeah, that would be really nice. We could.
Okay. So let's see. I'm gonna pick up my. Gonna try to write this out myself, so I don't say anything stupid. But I feel like. Let's see. Because what do we have? We have n over 2 n plus 1 minus a half. I mean, okay, yeah. there is, I think, an easy trick, right? So the thing is, this n over 2n plus 1 as a fraction, if you divide both numerator and denominator by n, then you get 1 over 2 plus 1 over n. And this thing, here you can easily apply the limit rules to see that this thing converges to a half.
1 over 2 plus 1 over n?
So you have this n over 2n plus 1.
Yeah.
You can divide both numerator and denominator of that fraction by n. That's all.
I see. Yeah. And then you get a half plus 1 over n. N plus.
Well, you're careful. Like in this, you get this 1 over, and then in the denominator, 2 plus 1 over n.
1 over, and then in the denominator, 2 plus 1 over n. Oh, I see. Yeah.
Yeah, that's all.
2 plus 1 over n. Okay. Yeah.
And now it's like, it's kind of, how do you want to argue? It's kind of all the same, right? Because we have now the absolute value, or I guess, yeah. So for this term, right, this infinity norm, because of this argument, like this infinity norm for this particular term just comes down to the absolute value. So we have the absolute value of this, and we want to show, right, there exists in capital N big enough such that blah 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 blah.
Yeah.
But showing this is literally the definition of showing that the sequence 1 over 2 plus 1 over n converges to a half.
1 over 2 plus 1 over n. Right. Yeah.
Like, it's literally just the epsilon n definition for that, right?
Yeah.
So and
yeah.
for that one, we know by the book. So we kind of argue backwards. We say, okay, by the limit rules, we know that 1 over 2 plus 1 over n, this as a sequence converges to a half. If you write out the epsilon n definition, this gives you exactly this thing in absolute values, right? There exists a capital N big enough such that blah blah blah.
Yeah.
And that's exactly what we needed to get this thing less than epsilon over 2.
Okay. I see the argument. Yeah. I guess
Yeah.
to write that out formally, like.
Yeah, so to write it out formally, you really need to start backwards. So you start with saying, consider this sequence, like 1 over 2 plus 1 over n. We know by this and this and this limit rule that this converges to a half. Writing out what does that mean, just with the definition of convergence. This means something in terms of there exists capital N such that blah blah blah. And that's, yeah, and then you'll see that just exactly what we need. Johnny German League have been exposed. But I'm on the kind of German. I'm still kind of surprised that like people think my English accent is more German than my other language. I always thought it's like the other one, but I'll not give it away. I'll let people think about it.
You seem pretty German to me.
Thank you. No, I've been worried because I don't live currently in Germany or have been brought up. Like, it's just my parents speak in our German and I speak with them, but like I've been barely speaking German whatsoever. for the last few years. So that my English accent is still German, I'll take it as a compliment that my German hasn't gotten worse.
Yeah, what is it? Is it Dutch? Belgium?
Yeah,
Belgish? Dutch.
you don't mind.
Dutch.
Yeah. Yeah.
Yeah. Uh,
Sound really Nordic. Yeah, Ilo Milo locked in. What the fuck?
yeah. Man, it's great to see how many people are just like on YouTube wasting their time.
Okay. You're guiding them with the true locking session.
Yeah. Yeah, you really got to focus on analysis. So yeah, that is kind of a beautiful argument. It's like by reverse invoking the definition, you can say that there exists an n.
Exactly. It's like all this, the hard work you did earlier, right? For like proving limit rules and so, like it finally pays off. We can actually use it.
Yeah.
Um,
Yeah.
so there exists this capital N, such that, yeah, I guess you have to write it out, but so you want that this, yeah, for all of these things.
Yeah. Yeah, here's a lot you have to write out. There exists an n such that n greater than n implies.
So we want that this absolute value of this sequence thing that we have minus a half is less than epsilon over 2.
Right, but we have in this case 1 over 2 plus 1 over n.
Yeah.
Implies it's less than epsilon. And then using that fact.
Minus a half, right? Inside these absolute values, right? Because it converges to a half.
Right, yes.
And we can say we less than epsilon over 2, right? Because we chose this epsilon beforehand, and it's epsilon over 2 is again some positive real number.
Yeah.
So we apply this urgent definition not to epsilon, but to epsilon over 2. And we say that our capital N that we find makes it so we can find it smaller than epsilon over 2. Exactly.
Yeah.
So now we have this for all these small n. And then we just kind of multiply both numerator and denominator by small n in this on this one side. And then we get exactly the logical statement that we want. There exists capital N such that for all small n bigger than n. Yeah.
Right. Yeah. We get we're gonna get n over 2n plus 1 less than epsilon halves. And then we have like, are we gonna have to do the same thing on the other one with cosine?
Yeah, but the other one I think will be a slightly easier argument.
You think so?
I think so. I think we will not have to use this trick. I think we'll be even more direct.
Really?
I mean, I haven't thought it fully through, but I think so.
Yeah.
Just like confound it easily. That's really nice.
Yeah.
Because okay, so now this other term, because I mean we have to do like one more thinking step, because here, right, our expression is dependent on x. So we have to kind of think about for a second, like what does this supremum norm do? It says like as we let x vary over the whole real line, how does the absolute value of the inside expression vary, or what is its supremum? Sorry.
Yeah.
But we can bound this supremum by bounding what this cosine is.
And cosine is already bounded, so we're gonna be between -1 and 1.
Exactly, and we're taking like in this definition of the infinity norm, we're taking the absolute value of the expression. So it's just bounded above by 1. It's absolute. So what you can say is that the infinity norm of that expression
Yeah.
is because you can write absolute values are multiplicative. So you have the absolute value of the fraction is the fraction of the absolute values. I guess that's a technical in-between step. But after that, so that's an equality. And then you can say since cosine blah blah bounded, that thing is less than or equal to 1 over 2m plus 1.
Yes. Oops. Less than or equal to an x. Oh, it's less than or equal to. Oops. We don't actually have the cosine. We can just say 1.
Exactly. Yeah, and here you don't even need any kind of brackets anymore, right? These theories are already gone in these in-between steps, like passing from infinity norm.
Oh, yeah. I see.
Yeah, right. That's kind of like letting this vary over all x and saying the absolute value has to be bounded by 1. This already tells us like, yeah, this takes care of the infinity norm. And then I guess very, very technically we get 1 over absolute value 2n plus 1, but that's positive, so we don't care about the absolute values.
Yeah, I see. Okay, and then what we can do is what you were saying earlier and use like a max.
Exactly. Yeah, we're technically right, but this one is much easier. For this one, we still need to find like, we want to bound this above by epsilon over 2. So you still have to find a capital N for this one, but this is much easier. You can just rewrite it.
Yeah. Bound above by epsilon over 2. And what n could we pick to do that?
Exactly. In this one, I would simply rewrite this final inequality that you want to express n in terms of epsilon.
Yeah. Which would be try to do this in my head, which is probably not wise.
Yeah, that's dangerous. That's playing with fire.
Yeah. Um, yeah, I guess.
Project Albert Austin is in here. I didn't recognize them. So used to like the Discord colors of people, like their names.
Yeah, I
So
know.
weird to see them.
It is weird to see that. Yeah, yeah. There are a lot of people in here.
Yeah, it's a lot of people from this.
Yeah. It'll be. I'm really interested in seeing like what will happen like 5 years down the line. Like one of these people is bound to be. I don't know. It'll just be cool to like talk to everyone like when they're more into their professional work. Like, will you be a professor in 5 years? Who knows?
Well, that would be kind of crazy. Like best case scenario, like best case scenario, I'll have finished a PhD in 5 years. I mean, if they offer me a professor, I won't say no. But
Yeah,
who knows?
yeah,
I mean, yeah, no, but I agree. It's cool.
yeah, yeah. It'll be that's I'm hedging my bets, so I'll be friends with a bunch of professors in a bunch of years.
I mean, to me, to be honest, I do see like being a professor is it's kind of bleak. Like also like I don't know, it's like even getting a PhD is kind of hard, and then you have to get a postdoc and enough postdocs and do really well, and then get an assistant professor and associate professor. It's kind of crazy if you think about it. It's so ridiculously hyper competitive this market for no reason.
Yeah, yeah.
Yeah.
D- Uh,
Maybe I'm just a bit salty, but it's gonna be hard. But yeah.
yeah, there's definitely like a lot of I feel like everyone feels this, like just kind of a pressure because of the competition of like I don't know that especially in stuff like math, like you really once you get down to like the final showdown for positions, like everyone you're competing with is just insane.
Yeah, yeah, that's kind of true. It's okay. There's these people in Germany. It's we call them the German machines. It's really not funny. Like how much shit they do in their masters and undergraduate, and they're like so hyper specialized already. And
Yeah.
then you finally find a position that you would like to apply to, and then there's some guy from a university from like a town with like 500 people that you never heard of, and he like basically studied this thing already for 3 years and studied and published 2 papers about it. It's not fair.
Oh no. Yeah, I feel like everyone is kind of hitting that because it's like e- everyone wants like the most cracked top of the line individuals. This is the same thing for programming. Like everyone wants the quant devs, but like the reality is a lot of people are just like not gonna be that insanely cracked. It sucks how the world has gotten so cutthroat and like forces you into
Yeah,
yeah.
I mean, somehow in academia, it's also like kind of understandable. It's like to some level, right? It's like you only need so many people teaching math full time, right? And there's just a lot more people who want to do that
Yeah.
than there are like a reasonable positions. So yeah. Mm, it's hard. Yeah, what Project Arc was saying is kind of interesting. It says he teaching or he does what no boot camps at a community college. Yeah, I would really love to. Them like sometimes I think about going to the US for a PhD. I think it would be more not necessarily easy, but more reasonable to find a position there just because the system is like slightly bit different. And this concept of a community college, it doesn't really exist here. That's
Hmm.
also a bit sad. Like I would love to just go to a college and teach people math who are interested.
Yeah.
Sounds great. Doesn't have to be like a fancy ass university. But like this whole concept of university college, community college doesn't really exist here. It's like only the big universities exist, and yeah, they can only have so many professors and PhDs.
Yeah. Yeah.
Yeah,
I mean,
yes,
yeah. It's a tough world for math lovers for sure.
true, true. Um, okay, let's not get too depressed and let's bounce some.
That was all too real.
Like, it's so fine. I think about this every day. I'm used to it.
Um, yeah, so
Okay,
how do we solve for
right.
this exactly? Like, how would I set this up to be, um,
Actually, yeah. So we want to solve this final equality. So we want n in terms of epsilon. I don't know. To me, it's like there's one way that's screaming to me. Just do the algebra. That's very helpful, I know. Um, I would say multiply both sides by 2n plus 1, and then divide both sides by 1, and then you're almost there.
okay, yeah, I just,
Yeah, and I wouldn't try to do it in your head. Just yeah.
um, 2n plus 1, and then divide by, and then subtract 1, divide by 2.
This is so cursed that you're doing this in the line where you also have your other inequalities. Next level.
Yeah. So we're gonna get, and we're gonna get a 2 on the bottom of the epsilon. Minus 1/2 epsilon.
Yeah.
2 epsilon. Yeah. Minus 1/2 epsilon.
Exactly. And a 2 in the bottom of the epsilon. Yeah, exactly.
Yeah. Okay.
Brackets,
Yeah. And then we can just pick an n
uh,
greater than that.
exactly. And you should put the epsilon in the denominator also. The fraction kind of popped out.
Oh. True.
Yeah.
Yeah. Okay, cool. Yeah, what the heck, Project Alec? Alrighty. So
Okay, so you choose, let's say, called M prime or something.
big N prime.
Big N prime, such that it satisfies this condition, right? It's some natural number such that it's bigger than that.
Well, shouldn't it just be equal to that? Like, and then the N will be.
Well, but like this N, it doesn't have to be like where this epsilon thingy doesn't need to be a natural number. It could even be negative if epsilon is very big, right? And it doesn't need to be a whole number. So just say pick a natural number bigger than it, and then you're good always.
Okay. Yeah, that's you got to be very rigorous.
Yeah. So you choose the capital N natural number bigger than that. And this inequality in the line above, it's still crazy. Okay.
Yeah, I probably should clean that up a little bit. Yeah, that's. But
So
I mean,
then, right? Yeah, sorry.
it's not technically wrong, right? It's just like really.
Well, yeah, kind of is. I mean, if we're really looking at what is that sentence saying? Since cosine of 1 is bounded by 1, cosine is bounded by 1, we have that infinity norm is less than that, is less than n. Nah. Nah, that's not it.
Yeah, okay, yeah. I see.
Yeah, so in that line, you don't even necessarily have to mention epsilon. So you only have that cosine infinity norm thingy is less than 1 over 2n plus 1. Then in your next line, you choose your capital N such that blah, blah, blah. And then you say for every n bigger than this capital N prime, we have 1 over 2n plus 1 smaller than epsilon over 2.
Right.
Oh, wait,
Yeah,
we started with epsilon as a 2, right?
We started with what?
Wait, I think we kind of fucked up. Or not that badly, but we had this 1 over 2m plus 1 less than epsilon we solved. But we wanted it less than epsilon over 2.
Oh, right.
Doesn't change that much. Let's see
Yeah.
what would change. You get 1 over. I think you just remove the 2 in the denominator with the epsilon.
Wait, so maybe Project Elk was right.
Maybe cooking. I didn't read what it was.
And then we've got.
No, he has it in the other one. Yeah, should be that. I think I also do it in my head, so it could also be very wrong.
Yeah. I feel like I trust that though.
Yeah, no, I think it's fine, right?
Wait, so the 1/2 was.
Yeah, yeah. So you choose this exactly, and now you have for every small n bigger than capital M prime, you do have that 1 over 2m plus 1 is strictly less than epsilon over 2.
Over 2 plus 1 is
And
strictly.
I think I have to add what's correct. This definition for your n prime.
You what? Sorry, you're a little muffled.
Sorry, this thing you had before for your n prime was correct. So 1 over epsilon minus a half.
Even with the epsilon over 2 factor.
Yeah, yeah.
So n greater than
wait.
prime.
Get 1 over epsilon would be n plus a half. Yeah, it works.
N greater than, which means that n 1 over 2n plus 1 n is greater than 1 over 2n plus 1, which is less than or equal to, or greater than or equal to.
No, for some reason the stream is kind of behind for me.
I thought you Germans had good internet infrastructure.
Well, I don't live in Germany.
Oh, true. Yeah,
Uh,
yeah.
but I also know Germans are terribly behind on digitalization. It's crazy.
Oh, really? Huh. Yeah. So.
So let's see. There's this middle inequality should be an implication error, and something is a bit funky here. We do have n being strictly bigger than 1 over epsilon minus a half, but that should imply 1 over 2m plus 1 being strictly bigger than epsilon over 2.
Yes. Strictly
So
bigger than epsilon over 2. And we know that this is greater than or equal to the inf norm.
Exactly.
Okay.
Maybe I'm a bit behind, but the order of the inequalities on the very right is a bit flipped. As in this, you have this inf norm, which is less than or equal to 1 over 2 plus n, and that should be less than epsilon over 2.
Inf norm is less than, and that should be less than. Oh, okay, okay. The epsilon over 2 is the very last thing we need to show.
Exactly. The biggest one. That's what we want to bound by.
Yeah. Okay.
Okay.
And so now we have the two different parts. Are we going to combine them with a max function?
Perfect. So yeah, can you see the whole argument? Wait. What you've written down now is epsilon is the smallest. Epsilon over 2 is the smallest one. We want it on the other side.
Oh, yeah. Yes, choose a natural number and epsilon over 2. On this side of the implication. Oh, wrong. Wait.
Wait a second. Yeah, that's what we want. So we have this, right? So this is for these small n bigger than m prime. And we also have something if small n is bigger than this other capital N that we had earlier. And now if we choose a new n, something, n double prime or whatever to be the maximum, what can we say? Or how does the argument conclude?
Well, we know that since anything like greater than n double prime, like n greater than n double prime is both greater than either of the component n's, like n and n prime.
Yeah.
Yeah, so yeah, which would act as like a bound for either thing. I don't really know how to say that formally, I guess.
I mean, the first part, that's definitely what we want. So because small n is bigger than capital N, we know that the first inequality holds, right? Because this first thing that we did is like it's just a formal statement for all small n bigger than capital N,
Yeah.
the following inequality. So we just, if n is bigger than capital N, we have in particular that small n is bigger than, if small n is bigger than n double prime, then we know that small n is bigger than big N. And therefore, by what we did before, this inequality holds. And then the similar thing for the n prime.
Yes. It's a cool trick with max.
Yeah, in some sense, yeah, it's not very special. It's like just a handy one. It's like, how can you encode an and statement with like bigger than or something? Yeah.
Yeah.
It's just fine to just write, you have this n and this n prime, and then say, oh, there exists a double n prime which is bigger than both of those, or at least as big as both of those. Choose one of those.
Yeah.
Well, the max satisfied, so might as well choose that.
Cool. Yeah.
So the second one really holds, and I guess you should finish it, right? So you have this the sum of infinity norms is strictly less than epsilon over 2 plus epsilon over 2, and that's epsilon, and then you're done.
The sum of infinity norms. Oh, right.
Yeah, so you kind of finish the inequality that you started earlier above.
Let me grab. I should be able to do like a reverse lookup with the types preview. Does that work? It
You
does.
should be able to refer to it. I don't know how to do it in tips. But, I don't know. In tech, you can, if you put an equation in an environment, you can give it a label and you can refer to that label. It's probably similar here.
You can, yeah. They have a way to do that, but I'm just like a caveman copying and pasting.
Yeah.
Since that's less than. Oops. And the sum. Oh, why is this multi-line? That is ugly. There we go. Okay, so then the sum of them is less than epsilon. Okay.
Yeah. Exactly. And this is, yeah, going all the way back, this is what we wanted to show, right?
Yeah.
If we chase back through this triangle inequality, we have found this double N.
Yeah. Cool. That was a bit of an arduous problem, but oh well.
Yeah. Yeah, it's I mean, it was a good one for getting back into real analysis, I think. Right?
Yeah.
A lot of old stuff needed to be uh dug up.
Yeah. Yeah, I think so too. Definitely had to. There's a lot of like, I mean, in this homework right now, it's probably getting probably late in your time zone. Um, there's a lot I have to teach myself that I kind of glazed over. Like, what even is a Taylor series?
Oh, good question. Yeah. No, I mean, fuck. Yeah, this next one. I mean, I think I know what they mean, or I do know what they mean. The question is like proving that everything works. Oh fuck! I forgot all the theorems. This is the stuff that you. I mean, right? Okay, so I can tell you what the move is gonna be. So you want to find a series representation, and what they want you to do is use the Taylor series for e to the u, which is the thing that they're given there. Plug this into the integral. Wave your hands, aka cite some magic theorem proven somewhere in the course that you can exchange the sum and the integral. So you get an infinite sum over integrals, calculate those individual integrals, and then you get a sum over things. That's what I want you to do.
Okay.
The thing is, it's not too bad. It's the only thing that you have to be careful in the real analysis course is justification about why you can interchange this integral with this infinite sum. And yeah, this has been a very long time since I had to justify something like that.
Yeah. I see. Okay. Okay, cool.
Yeah.
Would you have any idea of like
But
what that would be called?
it's probably fuck yeah, I automatically think of uniform convergence, but it's not. I forgot these things. It's somewhere like, because basically, maybe it's like a theorem, interchanging integrals and sums. Fuck yeah, how would you call this? There's probably some people. Didn't Project Alc use the same textbook as you or recently?
Uh,
You should know. Um,
yeah, I would source it to Project Alc.
so, I mean, in the variant, what it comes down to is interchanging limits, because it's you're interchanging this limit which defines the integral with the limit of the infinite sum. And there are conditions when you can do that, and this is like a very special case. Yeah, you should be able to look up interchange. Fair enough. That's a good one. 2019. Damn.
Yeah, that was ages ago in terms of
Yeah.
where the world is now.
Yeah, damn. People learning analysis in 2019. I wasn't even learning analysis in 2019.
Yeah,
It was
weren't you
basically
like 10 or something?
me 10? No. Wait. Hold up. That doesn't matter. Fuck.
Interchange.
Um. Da da da. Yeah, integral infinite sum. There's probably like a million conditions for when you're allowed to do that. I just don't.
Oh, there we go.
Yeah, exactly. Yeah, Fubidi Tonelli, sure, but you're not doing a course on measure theory. Fucking try arts, like. Yeah, that's true. It's overkill. And, um,
Success of.
I mean, before I saw something on your screen, yeah, power series. Okay. Hmm. What's your book called? It was Abbott, right?
Yeah, understanding analysis.
Let me see if I can just Google Abbott.
It should be free, yeah. What chapter? It's 6.6. Damn, that's why you're so wise. You can tell like when someone's like 10 years older than you, like no is also like this. They've had just more time to like read books. Like no matter how smart you are, like
True.
someone with 10 years of reading will always beat you.
Yeah, that's very true. That's very true. Um, okay, I'm looking at, but where in Abbott? They're saying that Abbott uses the also uniform convergence. If a series of functions converges uniformly, you can do this. But where in Abbott is this? Let's see.
A series of functions converges uniformly. Okay, so you need uniform.
Yeah,
Okay.
I mean, your thing is definitely gonna satisfy everything. It's gonna be completely fine.
Yeah, they're gonna make it real nice for sure.
Yeah, exactly. This thing that you have, like the power series for the exponential e to the x, it's like the nicest one there is, more or less. It converges really, really well. So it's gonna satisfy all the things that you want. I hate AI answers, man. I just looked it up on Google and I got the AI overview and says, "Oh, Stephen Abbott's understanding analysis. It uses uniform convergence." And then I look at its sources and none of them mention Abbott. That's fucking. I mean, we can also just skip it for now and just do the rest and just you can just make a note of this, like find the theorem in Abbott which justifies this interchanging step. Um, yeah, but it should be something with uniform convergence.
Why, like, what's the intuition between why, like, an interchange like that would work anyway? Because isn't an integral just like a super high definition or high resolution sum?
Yeah, I mean, an integral is a sum in some sense, but that's kind of you. I would rather think of it in this context as the integral as a linear operator, as in you know that for finite sums, if you have the integral of the sum of two functions, that's the same as the sum of the integrals, right?
Yeah.
And this is kind of saying like, what if instead of a finite number of functions, we have an infinite sum? And then when does this still work?
Yeah, I see.
And it says if your functions converge nicely enough, then you can still do this.
That's interesting that it's like nicely enough, like, but not if each of them is nice, but like kind of different niceness on its own.
Yeah. Well, yeah, that's the problem. I don't know the actual proper thing. I think it works very often. This integral, like, right? This is what these people in the Stack Exchange post that you had about, which talked about like Fubini's theorem.
Yeah.
Fubini's theorem is like something very general about interchanging integral, the order of integration, which is sort of similar to what we're doing here. And this works like in a very big generality in like measure spaces and general things like that.
Right.
So it works quite general, but not always. So you still have to justify it in some regard.
Yeah.
Um,
Yeah.
okay. Okay, so yeah, well, okay. Up to that step, we can just more or less literally plug it in, right? Because we have a power series for e to the u, and if we go, what was the exact question again? E to the minus x squared or something?
Yeah, you to the minus. Yeah, exactly.
And what exactly? How much proof that the series converges
Two.
to the in? Yeah. Okay. So I guess at some point or at the beginning we should mention that that this uh how do we want to say this, like this power series for e to the u, right? This is going to converge on the whole real line. It's like a really good power series,
Yeah.
but we probably need something like this to justify that as a function, like let's say from the real line to the real line, like e to the minus x squared, to get a power series or a series representation for just that. We can just plug minus x squared into u
Yep.
and say this works on the whole real line. So this is probably comes down to, which is also probably somewhere in Abbott in this power series chapter as an example or an exercise, like, and if it starts talking about like radius of convergence or something like this, about this exponential one that it converges on the whole real line.
Yeah, I see. Yeah. Um, so
Um,
it seems simple enough. It's just like finding the conditions and then swap
Yeah,
them. Yeah. Okay.
yeah. So again, up to that, right? We can say that e to the minus x squared. We may write that as the sum from n greater or equal to 0 to infinity of minus x squared to the n over n factorial. And then we take the integral of that, right? Then we take the integral of that. Then we have to mention, oh, by this and this property or convergence property, we're allowed to interchange the sum and the integral. So we get the sum from 0 to infinity of, let's see, integral of 0 to 1 of minus x squared to the n over n factorial.
Yeah.
Well, and that's just like that's an easy calculus one integral.
Yeah. Yeah. That shouldn't be too bad.
Which, yeah, I think you're allowed. I mean, I hope you're allowed to use your basic Calc 1 rules for these things.
Should
I
be.
assume. I don't. They want you to prove that from scratch.
Yeah. Is it true that you kind of learn like I've heard in some countries they don't really do calculus, they just always do analysis up to proving how the calc things work.
That's true. I haven't done this because I did most of my education in the Netherlands. But I know they do this in Germany, where the first semester of university, like first year, it's just fucking real analysis. Here you go.
Yeah.
And I think, I mean, I didn't go to high school in Germany, so I can't speak for that. But I'm pretty sure you do some calculus before that, right? Like at least like derivatives and stuff, and probably some integrals.
Yeah.
So you do have some kind of idea, like what are you getting into? What are we proving? It's not like it's gonna come like out of nowhere that you've never seen a limit, and then you're gonna do real analysis. That would be that would be mean.
Yeah, that would be absolutely brutal. Yeah. Um
But yeah, but here, I mean, we did do one semester of calculus in uni, and then real analysis.
yeah. Yeah. I kind of think also like you can do classes that are like way harder than or people can are capable of doing things that are way harder than they think. It's just kind of a matter of mindset in a lot of cases.
That's true. It's yeah, kind of that, and it's also like yeah, being in an environment where you're kind of forced to definitely helps.
Yeah.
Also, in the case like yeah, okay, maybe you won't get like a perfect grade or like remember all. You will still learn a lot more than you thought was possible beforehand.
Yeah. Yeah, totally. Yeah.
Mhm. But yeah, it depends all a bit like on the schooling system, right? Like just like how American colleges are kind of set up. It's not really the purpose. I feel like it's right. It's more towards this liberal arts kind of thing.
Yeah.
You just don't have that much time for everything, so it makes sense in that aspect.
Yeah. I see. Yeah. If you ever come over here to do a PhD program, you're going to be slammed by the American techno capitalist mindset. You're just going to be optimizing for value 24/7.
Yeah, I'll see. Maybe I'll try to unionize the department. Who knows? Let's see how.
Yeah.
I've heard great things about unions. But it is, yeah, yeah, yeah. People will rise to the challenge if you challenge them. Very true. Keeps lowering.
Yeah.
Yeah, yeah. There is some truth to that. But yeah. Mm. But I mean, on the other hand, some countries also like keep raising the bar, and that's like I'm thinking of like Asian countries, like particularly China.
Yeah.
I've recently like a video, like a part of a podcast about people who were there, and they talk to people there, and like people, let's say in their 30s or something, or like in China who have kids of their own going to school and stuff, right? And they're seeing like, yeah, like back then we studied hard, but now our kids, it's crazy. They have to study so much harder, and it just keeps going, and it's kind of getting out of hand.
Yeah,
So it's kind of like another side of it.
it is kind of weird how everything tends to drift towards being like broken after a while. Like it either gets too low effort or too high effort, and then bad stuff happens. Like, why can't people just stay
Yeah,
kind of in the middle?
yeah, it's difficult. I mean, there's probably like a million other factors, right, that I'm not even thinking of. But I feel like, I mean, I'm slightly biased, of course, but like where I'm saying it's quite nice. Like I'm definitely definitely challenged throughout my degree, but I mean, it's nothing like that. I'm like working 10 hours a day every day for like years, something
Yeah,
like that.
yeah,
Damn. As long
yes.
as they don't miss 50 total days per semester, they get a C automatically. Damn. That's okay. Well, yeah. Okay, maybe I underestimated the power of the American public school system.
Well, I've also been seeing like a lot of grads now, especially with the AI thing, like getting out, and senior engineers are starting to adopt like AI harnesses, and it's not just like that people don't have skills, it's like that they just weren't willing to learn in school. I don't know, and it, it,
What do you mean with AI harnesses?
like junior software engineers are really in danger right now because um, the like AI dev
Yeah,
tools are just so good now, and you see like
yeah. Like, yeah.
there's
What
all
I see on
these.
the server, right? Oh, oh, I feel like you're kind of cutting out. Maybe it's,
No, go ahead.
I don't know. I don't know. I think it's fine. What I see on the server with like people and like how they talk about AI, and every day there's like literally 20 new acronyms that I've never heard of, and it's some new AI shit. What do you guys think of this? It's like I almost get burned out just listening to you guys. It's fucking crazy.
Yeah, it's bad. I can't even watch like AI dev tool news without just being really depressed. So I decided like I don't know. I'm just gonna chill out. Whatever. Like if the capitalist god at the end of time appears and consumes everything, it's out of my hands at this point.
I think that's very good. It's something really. Yeah, no, no, really. Like, I also, if I watch too much of the news and all these things, I like also get kind of depressed. So it's very good to touch some grass in between.
Yeah.
Um,
I think the problem is easier than presented. You don't know about integrals yet. That is next semester, so you'll need to maybe just substitute the given series. No, I'm pretty sure that I do know about integrals. I mean,
yeah, actually, either we. Who's we? No, um, no. I mean, we more or less, yeah. We substitute indeed. We substitute this minus x squared for u. But I'm pretty sure like this is what the problem is, right? They want you to do this substitution, but most importantly, they want you to justify like all these interchanging steps, like we can interchange from an integral by yada yada yada, and this thing converges still on the real line because of yada yada yada.
yeah, yeah, I see. Um, so can you swap the? What do they ask you about swapping the limit and the integral? Um, like
Uh, Wait, sorry, what do you mean? Like when?
question three. I mean,
Ah, okay. Can we solve the limit and integral for? I hate that they write it out in words and are imprecise. Just write out the careful statement.
yeah,
Okay.
this it's not the most serious
Um,
real analysis class in the world.
well, I mean, let's see. Okay. I mean, okay, so my first thought, if they ask the problem like this, the answer is most likely going to be no, and we're going to find some kind of counterexample. So let's try that one first. As in, let's think about first, what if we take the limit of this function of n goes to infinity? We're going to get a pointwise a function of what's it going to look like?
Yeah, what is it gonna look like? Because we get a negative n. Yeah, that's a little weird. I can't tell immediately what that'll.
Okay, yeah, so we fix the x, right? And so we can pull out the like e to the minus x squared to the n, and then that's some number, and it's going to be a number less than or equal to 1.
Yeah. Yeah.
And if we're going to raise that to higher and higher power, so that's going to get smaller and smaller. And we're going to multiply by n. So it's kind of like this multiplying by n times a constant to the power n. And this constant is going to be less than or equal to 1. That's kind of how to think about it.
Yeah.
So there you can kind of, right, by intuition, like this exponential in some sense grows faster than this n. Or I mean, that's not really the right way to put it, right? Because as this exponential gets smaller and smaller, but it does this much faster than this linear thing. So this product is going to go to 0.
Yeah.
I'm pretty sure.
Yeah, I think so too.
Yeah.
Yeah.
And I guess we have to be a little bit careful because I said e to the minus x squared is less than or equal to 1, but it's only ever 1 if x is equal to 0.
Yeah.
Then we get 1 to the n times x, but x is equal to 0, so the whole thing is 0.
Yeah.
So in this case, it still goes to 0. So I think what happens here is that this function pointwise converges to the 0 function, the constant 0 function.
I agree.
So that's one thing. And so yeah, it's a nice and easy example, I think, because now they're asking us if we can interchange sum and integral, limit and integral, but this if we first take the limit, we get identically 0. So if we then take an integral, well, that's just still 0. But if we first take the integral and then the limit, we just have to show that that's non-zero, and then we're already very happy. Because then we have shown that they're not equal, and that's kind of like the no output from them.
I didn't get
Like
what
the
they were
top one.
asking at first. This is really weird. Like,
Yeah, they should have written it down more carefully.
yeah. I see. So yeah, we just have to show that if the integral is on the inside, we'll get a non-zero value essentially.
Exactly.
Nx e to the nx squared. Okay, on 0 to 1. And we can just take, what are we taking the derivative or the integral with respect to? X, I guess?
Yeah, with respect to x, but then we take the limit of this whole integral thingy. Because you take the limit, the integral with respect to x, this is going to be something in terms of n, and then we take the limit as n goes to infinity, and we want to show that this limit is non-zero.
So what we were showing before is essentially like the other version of this, like the integral from
Sorry?
0 to 1.
You kind of cut out. What we were showing before was first taking the limit and then taking the integral of that. That's actually equal to 0.
Okay, where? Point-wise.
Yeah.
This is
So
really
yeah.
awkwardly written out, but yeah, we're just gonna get 0.
Yeah, wait, I'm a bit behind. Yeah, no, that's what you want. Exactly right. The function, the limit of the function is identically 0. You should make your function f dependent on both n and x, not only n.
Oh, right, good call. What's the difference here between, like, why do they do a subscript in the n as opposed to, like, or oops, it should be like this.
That's not that deep. It's more like how you think about it. It's like for every n, we have a function in terms of x. And we think of n as more as a discrete parameter. But if you look at the definition, it would also make sense to think of n as like a continuous parameter. And then we could think of it as a function of like r times r to r, right?
Yeah.
But it's more like, oh, we think of it as a discretely parameterized family of functions in terms of n. Yeah. But you're right. Otherwise, like it's just how you think of it. It's no real difference.
Yeah. Okay, cool.
Exactly. So you want to show that limit is non-zero.
Yeah.
Yeah. And yeah, if you did one, you can actually, with your basic calculus rules, you can evaluate that integral. And then you'll probably just see that you get something non-zero.
Yeah, which would be like, I mean, let's see, we're going 0 and 1. And in here, we can basically ignore oh man. Yeah, basic calculus rules, but it's been a while since I've done the antiderivative. Is this gonna cancel nicely, or are we gonna have to do some like integration by parts?
I think you're gonna have to do a use substitution.
Substitute. Yeah, because yeah, x squared, and then it'll cancel. Yeah. Okay. That makes sense. And we're gonna get u, well, 2u, and so we'll get like n halves. E to the u, negative n halves, du.
But I have to also do this thing in my head.
Is that correct?
I mean, wait, your face cam is kind of blocking it partly. But what exactly is the substitution?
I did x squared as the substitution, and then or
Okay, yeah.
or negative
I
x
mean, you could
squared, I guess.
even, I guess, yeah, but maybe, right? But I think now an n has been lost in translation, right? Because now then it should be e to the minus nu.
Oh, you're right. You're right. You're right. But could I do n in the substitution as well? Could I make the
Yeah, yeah. Right? That's fine. You can say u is minus n times x squared. I think that's even the best, because then it will also cancel, or probably maybe I'm saying something stupid, but I think it will also take care of the n, which
yeah,
is not
no,
in the exponent.
it will. Yeah. And this will be over 2. Oops. Yeah, so negative n. This whole thing will be negative, though. But yeah, it should cancel.
Yeah.
And then we'll get negative 1/2 of
Mm.
e to the u.
Yeah, seems about right.
Yeah. Um,
Yeah, and so the nice thing is, like, right? Technically, we're still taking the limit, but now this whole expression will be independent of n. So the limit will become very uninteresting.
yeah. Yeah.
So yeah, so now it's basically just calculating that integral. You just have to show it's non-zero. Then you have a limit of a constant thing. It's non-zero, so the limit is non-zero, just equal to that thing. And then we have shown that the two things are actually different.
Yeah, and the antiderivative of e to the u is just e to the u.
Yeah, yeah. That one's important. Yeah,
Yeah. And
exactly.
yeah,
You're gonna
so
get e line for that integral.
so we're gonna get like negative 1/2 times e to the. We're gonna have to substitute back in. Uh,
No, because you've already, well, wait. We have to worry about the bounds of integration, of course. It's been a long time for both of us, this calculus. When we do the u substitution,
yeah.
we should have thought about the bounds of integration. Um, like,
Uh,
right, if x is 0, what should u be? U will still be 0 because it's minus x squared.
well, couldn't we substitute back instead of doing bounds of integration?
I think that makes everything more complicated. No, we kind of do have to do the bounds of integration, right? Because, yeah, otherwise just the bounds that we're evaluating the integral are just not the right ones.
Yeah. Yeah, so 0 makes sense,
So
but what would the 1 become?
x is equal to 1, and then we get at the top minus n. So it will still be dependent on n.
Why
But it won't be
minus
that.
n?
So it's just like u is defined to be minus n x squared. What happens if you plug in x equals 1?
Oh, yeah. I see.
Yeah, top u value. So you integrate from 0 to minus n. Well, yeah, that's still not bad.
And
Um, so we should. So then the integral that we get is minus a half times e to the minus n minus 1. So this new expression is still dependent on n, so we should put back the limit everywhere, but it will be easy to evaluate.
yes. I'm just going to do this, which is a little bit cursed, but I want to write that out a bunch of times.
Oh, I already know what's coming. Oh God.
That's kind of
Yeah,
abusive notation a little bit, but
yeah, a little. I mean, sometimes you have to keep the graders on their toes a little bit, you know? You can't make it too easy on them.
yeah. Yeah. Plus, this is undergrad. They're expecting stuff like this.
Fair enough. I mean, I don't know. Sometimes it feels kind of like different for me, but like at the beginning, like proper proofwriting technique and carefully writing things down was really like fucking drilled into us, and they were not fucking joking about it.
Yeah.
And then the further you got along, the less fucks they gave. And then when I transitioned from like bachelor's to master's, it was like hand in some assignment where I barely had any time, you know, and it's like half-assed, like, oh fuck, what grade am I gonna get? And in the end I got like full marks. It's like, what the fuck is this? They don't care.
Yeah. And I like Euclid just wrote down like poetry basically.
Yeah. Yeah.
So yeah, that limit is gonna be just that e is gonna go to 0, so we're just gonna get 1/2.
Yeah. So I guess in this case, where n is gonna go to no, yeah. Sorry, I was about to say something stupid. Yeah. It's gonna go to 0 indeed. So you're gonna get a half indeed.
Yeah. Uh, and then I can just wrap this up with pretty obvious since 1/2 does not equal 0. Okay, cool. That was definitely easier. Good art.
Um,
That's what I'm saying, Project Elk. I never thought about changing the bounds of the integral. I always just subbed back once the algebra was done.
what is it? I mean, if you do like a what's it called? Fuck. What's it called when you don't have the bounds? Oh, an indefinite integral. Then you kind of always have to do that. But I don't know. If you have a definite integral, you can just substitute your way through. I think I don't know. For me, it's always easier.
Yeah. Yeah. I see that
Mm,
now. Okay.
okay. Well, we can kind of look at one more, see how hard it is, or maybe give you some pointers, and then I think I'll also have.
All right, cool. Yeah, I should
Um,
probably eat soon too.
this one seems nice and general. That's good. No explicit formulas involved. Um,
Yeah. To function, prove that f is
wow.
continuous. Oh, okay. Okay.
Damn. I'm already looking at the next one. They're kind of proving the fundamental theorem of calculus. Well, one of them. That's nice. Um, okay, prove that f is continuous. Well, so what does continuity mean? Let's see. For us, it means that
Can you
well,
pull up the definition?
I mean, you can use anything, right? You can use either, I don't know which one you've seen, right? This epsilon delta. It's like the limit as x goes to some x naught is of f of x, capital F of x, is f of x naught. That's epsilon delta. That's we could also, I mean, you can do a similar thing with like a series convergence. I guess it kind of comes down to the same thing.
Yeah, they're equivalent.
Yeah. Mm. Is it easier to do topological definition? I don't think so in this case. Won't be very nice. Talk about open.
Actually, yeah.
Um. Okay, so I guess we should fix, right? Continuity is something we prove pointwise. So we should fix some point in between 0 and 1. And we have to prove that the limit of this capital F of x as x goes to x naught is capital of where was it? Capital F of x naught. Yeah. Maybe, yeah. I don't know. Probably just a definition. It's. I think it will be something reasonable.
Yeah. Okay. Yeah.
Because you just plug in the definition of f of x. Because what are you gonna evaluate? You're gonna do like capital F minus capital F of x minus capital F of x naught, right? As x is some delta distance away from x naught. So you consider this difference in absolute values, and you want to bound this by epsilon.
Yeah.
And then I think, yeah, you just need you need like a little integral rule probably, right? That you can like, if the bounds of integration align, you can kind of chain the integrals together.
Yeah.
Right? So if you have like integral from a to b over some function plus the integral from b to c, it's the same thing as the integral from a to c. Something like this.
Okay.
And that using a minus in the integral, you can flip the upper and lower bounds. Because what you're going to get is like integral 0 to x f minus integral 0 to x naught f.
Yeah.
And then minus integral 0 to x naught. That's how I would do it. I would write it as just plus integral of x naught to 0. And then you can say, and then you can add up the two bounds of the integral, and you get some integral from x naught to x of f of t, like in absolute values, and you want to bound this by epsilon for any old bounded function, but that seems really reasonable, to be honest. Like, can you? I'm trying to think. Because what would be the easiest way to show that? Oh yeah, it's bounded. Oh yeah, that's really doable. Yeah, okay. You're gonna explicitly use this bound and then this delta. That's gonna be fine. Yeah.
Okay. It doesn't seem terrible.
No. Yeah, it's just like, yeah, just using the epsilon delta definition of continuity and actually like really using then that this function is bounded, and these, yeah, the only thing you actually need is these integral rules about like chaining these endpoints together and flipping them around with a minus. And once you have that, then it's fine. Yeah. Second one, let me see. Suppose it's continuous at some point. Prove that f is differentiable. Oh, that looks nasty.
Oh no.
I don't know. Yeah, just fucking calculus. I mean, derivative definitions. It's like Project Alc. You've done this not too long ago. What's a good way here? Because like the only thing I can think of is like the definition of the derivative, right? This quotient limit. Maybe that's not that bad. Probably isn't, but maybe there's a better way to do it.
Yeah.
I don't know. Have you seen about like the derivative like properties in class, like theorems?
Yeah. Well, I missed like 2 classes, so within that time frame, possibly. Yeah. I mean, I'm not sure. I guess yeah. But I guess I'll call it for today as well. This isn't good for a little bit.
Yeah.
Yeah.
Right.
So, yeah. Cool.
Yeah. Damn, the next ones look kind of terrible. What the fuck is poem 5?
Oh no. All right, cool. I'll see you all later, everyone. More math streams coming up
Okay.
soon.